Okay, so thanks everyone for tuning in once again. This week we have Venkatesa Chandrasekaran from Berkeley, who's going to tell us about his work on black hole entropy, energy minimizing states, etc. Ben, thanks so much for giving this talk, and the floor is yours.
Thank you. Yeah, thanks for having me. Um, so I'm going to tell you about some work that I did with my advisor, Rafael Busso, and another student at Berkeley, Arvind Shahbazi Moghadam. And then towards the end, I'll tell you about some more work in progress that I'm doing with another student at Berkeley, Pratik Rath. So this talk is mainly going to be about a confluence of two ideas about classical coarse graining of black holes, and also about energy minimizing states in quantum field theory and how they come together nicely to understand how coarse graining would work for semiclassical black holes, like evaporating black holes. So just to give you a bit of an outline of how things are going to go. So first, I'm just going to talk about the area law for the classical area law for black holes as a sort of motivational setup. And then explain this coarse graining prescription for where the area law comes from, and where the area of a black hole even comes from thermodynamically. And then describe like what happens if we then instead consider semi-classical black holes. And then sort of go on what looks like a completely orthogonal detour into this question of minimizing energy of states in quantum field theory and its relationship to entropy. And then I'll come back to this question of coarse-grained entropy and show how these two seemingly disparate ideas actually unify when talking about small perturbations, like quantum field theory perturbations on a fixed curve background, and make a general conjecture for what the coarse-graining prescription will be for semi-classical black holes in complete generality, and just describe some progress that we've made towards proving this conjecture. So let's start with the area law for classical black holes. So normally when we talk about the area law, we talk about the area law on the event horizon, where we say like cross sections of the event horizon, the area always increases with time. Now, what do we mean by the event horizon? Well, intuitively, we just mean it's the set of light rays which just barely can't make it to null infinity. And this is the thing which the famous Hawking area theorem applies to. But it's pretty well known that for thermodynamic purposes, we don't really like the event horizon. I mean, it's great that it has an area law, but it's teleological, in that you need to know everything that happens in the future to define a cross section of the event horizon at some particular instant that you care about. So for thermodynamics, that's not good, because thermodynamics is a statement about like a particular state at an instant of time. In particular, if we're interested in things like the area law. So instead, we're going to be working with something called a marginally trapped surface. A marginally trapped surface is a quasi-local notion of a black hole, which you can define on any given Cauchy slice, and it corresponds to the light rays, which just barely can't make it out at an instant of time. So if you imagine on a single time slice, it's some surface where in an outward going direction, the light rays just can't escape. You have to keep moving along that instantaneously along that null direction. And for this, an area theorem was proven in 2015 by Busso and Engelhardt. And the purpose of the initial part of the talk is to just explain where this area theorem comes from. What is the entropic interpretation for the area of this thing and why it grows? So it was a beautiful construction by Engelhardt and Wall in 2018 that explained exactly this question. So let me just explain a bit of the setup. So imagine we have a collapsed black hole. So a black hole formed from some collapse, and we have a surface sigma here, which corresponds to our marginally trapped surface. so K here is an outgoing null direction, L is an ingoing null direction. And the marginally trapped surface is one where the expansion of the light rays in the outgoing null direction at that instant is just equal to 0. Now, there exists some partial Cauchy slice sigma, which anchors to our marginally trapped surface here, and also ends on our boundary B. So here I'm imagining a collapsed black hole in an ADS spacetime. So it anchors to some, it anchors to the entire boundary B at some instant. So I'm going to ask the following question. If I know everything about the exterior of the black hole, then what is the most ignorant I can be about the interior of the black hole? And again, every time I say interior and exterior of the black hole, I'm actually thinking about the region that's split by this marginally trapped surface sigma. Okay. So we know that in ADS-CFT, if I give you a boundary state rho, then it corresponds to some particular black hole background. So that's the setup that we're going to consider here. And then we also know that there's, in this context, there's an HRT prescription, which says that the entropy of the state rho is just going to be equal to the area of some extremal surface that sits in the bulk spacetime. Okay, so now what we're going to do is we hold so we have this outer wedge here, denoted OW of sigma, which just corresponds to all the data in the domain of dependence of this exterior partial Cauchy slice sigma. So we take sigma, we find its domain of dependence, that's OW, and we're going to hold all of the geometric data in that outer wedge fixed. So we're not going to change that at all. And then for that reduced state on the boundary, whatever reduced state is on the boundary that corresponds to this subregion, this exterior region sigma, we just hold all the data fixed. And in a sense that'll become clear later on, we're going to maximize over our knowledge of our lack of knowledge of what's in the complement region. And this entropy I'm going to call the outer entropy of the marginally trapped surface. So again, just to emphasize, we just maximize over the von Neumann entropy, holding everything in the outer wedge fixed. Okay. So the main purpose of this work by Engelhardt-Wall was to show that the so we have this quantity here called the outer entropy, and what they show is the outer entropy of sigma is actually equal to the area of sigma. So in other words, they set out to show that our maximum ignorance of the inside of the black hole is precisely the area of the black hole. So that gives it a nice thermodynamic interpretation. I just want to emphasize that like this is actually a very old problem that they solved, which goes back, you know, like 30, 40 years, like actually telling me what it is the area of a black hole is coarse graining over. So it's a really neat result. So the way they do this, at least the main parts of it that we'll need are as follows. So you can show using the classical focusing theorem, the details aren't so important, but using the classical focusing theorem that the area of this marginally trapped surface sigma is always greater than or equal to the area of the RT surface associated to the particular state rho. So this basically just follows from the cross-focusing equation. If you just shoot out light rays that go back in time from sigma down to wherever the RT surface is, and then just apply the focusing theorem. Okay, so now the hard part is to show that there exists a space-time that you can construct where the outer wedge is held fixed, and you're kind of allowed to fill in whatever you want for the inside of the black hole. Construct a space-time where this inequality is saturated. Because if this inequality is saturated, then from the definition of the outer entropy, which is just the maximum of the von Neumann entropy, which is the maximum of the area. So if there's a state which saturates this inequality, then that tells you that the outer entropy must equal the area of the marginally trapped surface. So the way they do this is basically using the details here are not so important, but you use the initial value problem of GR, and you show that there you can just so you take your surface sigma, and you consider the null surface that emanates from sigma to the past along this k direction. So you go back down, and then you choose your initial data on sigma so that using the constraint equations on a null surface, you can always construct a geometry on a null surface which has vanishing expansion in the k direction. So this theta k is quantity, the expansion, is just equal to 0 everywhere on this null surface. And then you just use the other constraint equations, like the cross-focusing equation, which tells you how the expansion in the L direction evolves. You just show that from this initial data, you can always trace it back so that at some point you hit a surface which has theta L equals 0 as well. So essentially, they just use the initial value problem to construct a geometry on a null surface which has theta k equals 0 everywhere and lands on an extremal surface. Because theta k equals 0 everywhere on the surface, the area of sigma has to stay constant. So the area of sigma has to equal the area of the extremal surface that you eventually land on. And that's how they saturate this inequality. It's pretty amazing that you can take any black hole, this could be a completely time-dependent black hole, and just attach a stationary null surface behind it. But that's essentially what they show using the initial value problem. So this proves for us, using their construction, this shows that the outer entropy of sigma, the entropy over ignorance of the interior, is just equal to the area of sigma. Okay, so that is the classical story, and that tells us exactly how the area arises as an entropic thermodynamic coarse-graining.
Sorry, a question. Can you
Yes.
hear me? So in this construction, when you move backwards,
Yeah.
you construct a new spacetime, right? You construct a spacetime that for which like there's going to be this theta L equals 0, so theta k equals 0, that which you interpret as the bifurcation surface probably, or some sort of a bifurcation.
Yeah, the extremal surface would be like, you can imagine it's like a bifurcation surface. Yeah.
Yeah, so it's a new spacetime that has like something in common with what you started with, but it's
a new spacetime in the interior. So I go back to this picture. I'm shooting the light rays back here. So if you look at what it does is it constructs a new geometry in the inner wedge.
Okay.
Over here, but the outer wedge is always held fixed. I'm not messing with the outer wedge here.
Okay. Okay.
Yeah.
Thanks for
So
clarification.
Yeah. Okay. Any other questions? Okay. Cool. Okay. So that's the classical setup. But we know that in a lot of the interesting situations we're interested in, we can't just consider a classical black hole because, for example, if you have an evaporating black hole, and we know that the area law is violated. So we know that if we want to explain something like the area law, if we want to explain the thermodynamics of an evaporating black hole, then it's not enough to just consider coarse graining for the area itself. We need to be a little bit better than that. So the particular setting I have in mind here is just a usual evaporating black hole setup where, for simplicity, you can just imagine you have a eternal black hole background, and I'm just considering small perturbations on top of that, where like small Hawking quanta are being emitted. The exact details don't really matter right now. So yeah, the area decreases because of the important thing is there's negative energy. Locally, there's negative energy that's present in the space-time due to the Hawking radiation. So we know the way to fix this. Like the usual stories, you talk about something called the generalized second law instead of the area law. So you define this quantity called the generalized entropy, which is given by the area of the surface that you're interested in, plus the entropy of all the quantum fields in the exterior of that surface. So, for example, in this context, it would be the von Neumann entropy, the bulk von Neumann entropy of all the quantum fields reduced to sigma plus the area of sigma, as an example. And then Engelhardt-Wall in 2011 showed that a very important property satisfied by event horizons. He showed that the generalized entropy always increases along the event horizon. But again, all of this is just for cuts of this teleological event horizon here. And as we mentioned, we don't really want to think about that. So we want to come to what is a notion of a local horizon if there are quantum fluctuations like Hawking radiation that are present. Okay. So let's consider for simplicity, so this event horizon here is the event horizon of a, let's say a stationary, like a killing horizon, like a Schwarzschild black hole. And I'm gonna throw so instead of directly talking about Hawking radiation, let's consider a related problem. I'm just gonna throw some small amount of negative energy into the black hole at some time in the future. So these are just small excitations on top of the black hole background. So we know the event horizon is teleological, so its shape is already predetermined. But there's a question of where is the local horizon? What is the definition of this quasi-local notion of a horizon that I can track at every instant and not have to track only teleologically? So this was considered by Busso and Engelhardt in an older paper, where they defined something called a quantum marginal surface. A quantum marginal surface is just one which has a vanishing capital theta k expansion at some surface sigma. So the sigma is the marginal surface. So instead of being defined by saying that the derivative of the area is 0 in the k direction, it's defined by saying the derivative of the generalized entropy is equal to 0 in the k direction. Of course, in the classical limit, this would just correspond to the usual expansion, but now this also includes the effect of the entropy. So if you take sigma, the quantum marginal surface, and you were to track where it goes as a function of time, it looks something like this green surface. So until the excitations are thrown in, it's just going to basically coincide at the event horizon up to some Planck length difference. And then in the future, it'll start agreeing with where the event horizon is, because the event horizon already takes into account where the fact that the excitations have been thrown in, even if they're only thrown in the future. The Q screen only learns about them later on. So initially, the Q screen and the event horizon differ because it doesn't know about the excitations, and then later on in time, it starts converging towards where the event horizon is. So that's the sense in which it's local. It actually learns about the excitations dynamically, whereas the event horizon is just predetermined. And of course, a special case of a quantum marginal surface is a quantum extremal surface, which is one where the quantum expansions in both null directions vanish, so that the derivative of the generalized entropy in both null directions is just 0. So we'll need both of these things. Now, Busso and Engelhardt showed in that paper that there is actually a generalized second law along these Q screens. So not only do event horizons have a GSL, but so do Q screens. And it's this Q screen quantity, or this quantum marginal surface, that we're going to focus on. Because it's the direct analog of what Aaron and Meta considered. Okay, yeah, and just for bookkeeping purposes, just keep in mind that so this quantum expansion is just equal to the classical expansion plus derivatives of the the matter entropy that's outside of the quantum marginal surface. Okay. So the question that we're interested in now is simply how do we get the coarse graining for this quantum marginal surface? In other words, first of all, where does the GSL come from entropically? And what is the correct entropic interpretation of the generalized entropy of this quantum marginal surface? So note that one of the motivations for this is also in holography, we have a good interpretation for the generalized entropy of an extremal surface, a quantum extremal surface. This was proven by Netta and Aaron using the quantum extremal surface prescription. But we don't have an entropic interpretation of, or sorry, we don't have a boundary interpretation of the generalized entropy of any other surface. So part of the motivation here is to at least give a boundary interpretation of the generalized entropy of a cross-section of a dynamical black hole when there are quantum fluctuations. Part of that will involve figuring out what this coarse graining is. Okay, so to start with, let's just follow our nose and try to do the same thing that Engelhardt and Wall do in order to define an outer entropy that has quantum corrections in it. Okay, so again, so as I mentioned, Engelhardt and Wall showed a while ago that the generalized entropy of the quantum extremal surface is the thing which computes the von Neumann entropy of the boundary state, reduced to this, whose bulk dual just knows about the outer wedge. So now we will then define the outer entropy of our quantum marginal surface pretty straightforwardly as maximizing over the von Neumann entropy of all the states with the outer wedge, i.e. the exterior, held fixed. So earlier, we were only holding fixed the geometry in the outer wedge, literally the metric data. But now we not only hold the geometry fixed, we also hold the quantum state in the exterior fixed, the exterior of the quantum marginal surface. This is going to introduce some complications, and we'll see how to figure out how the coarse graining works in that context. Okay, so the easy part is so earlier we had this statement that the area of the classical surface is always greater than or equal to the area of the classical extremal surface. The analogous statement is the generalized entropy of sigma, the quantum surface, is always greater than or equal to the generalized entropy of the quantum extremal surface. And I don't want to get into the details of this because it's not particularly illuminating. And it follows straightforwardly from applying the quantum focusing conjecture and the quantum maximin prescription. So using these two things, you can straightforwardly just argue, very similar to the classical one, that the generalized entropy of sigma is always greater than or equal to the generalized entropy of the quantum extremal surface. So the part that I want to focus on is the harder part. It's doing something analogous to what Netta and Aaron did, or trying to figure that out at least, how to construct a spacetime and a quantum state that saturates this inequality. So we want to find a state and a geometry for which the generalized entropy of our quantum marginally trapped surface is just equal to the generalized entropy of the quantum extremal surface. Okay, so that's the setup of the problem. And now I'm going to slightly deviate in what seems like a totally orthogonal problem. But this totally orthogonal problem is what will help us answer this question of how to construct this spacetime. Okay. So there was a very nice paper that Aaron wrote back in 2017 with a very cute story attached to it. So I'm going to follow his story and explain exactly what the problem is. So imagine, so we're just in a 2D CFD right now for simplicity. And imagine you have an ant that starts at infinity. It starts at infinity and starts walking down towards -infinity. and it stops at some point x naught, some spatial point x naught. And we ask the following question. So given the knowledge of, so the ant has knowledge of the entire state of your quantum field in the region x naught to infinity. So it knows the reduced state in x naught to infinity. So given that knowledge, what is the smallest amount of energy that you can put in the complement region from x naught to minus infinity? So Aaron had a conjecture. He said that the smallest energy you can put from minus infinity to x naught, the stress tensor, holding fixed the density matrix rho in the region greater than x naught, this is what the ant has access to. So the smallest energy is actually equal to the derivative of the entropy evaluated at x naught. And when I say derivative of the entropy, what I mean is you move the cut x naught here a little bit to the right, and then that derivative you evaluate at x naught. So it's a derivative of the entanglement entropy at x naught. That he claimed was equal to this minimum energy. Okay, so let's study this conjecture for a little bit before we come back to the coarse-graining problem. In particular, let's say this conjecture is true. Let's just take for granted that this conjecture is true for a second, and then ask, what are the properties that the optimizing state has to satisfy? So when I say optimizing state, I mean the state which saturates this infimum. It's the exact infimum state. So let's study the properties of that. Now, before we move on, let me just point out that there was a paper by Faulkner and Ceyhan that actually proved Aaron's conjecture, and not just in D equals 2, but in all dimensions. And it was a very elegant construction that I will come to in some more detail towards the end. But for now, let me not mention more of it, because we're just going to study, they had an explicit construction. We're just interested in studying some properties of the state a little more abstractly. Okay, so in order to study the properties of the optimizing state, the infimizing state, there's just some usual facts about entropy variations that we're going to make use of. So the first thing is just that the relative entropy of this of the state rho in the left region, so rho less than x naught, so rho of the left region that we don't know about over here, we can decompose that as the vacuum subtracted modular Hamiltonian. So k of x naught is a modular Hamiltonian. So vacuum subtracted modular Hamiltonian minus the vacuum subtracted entanglement entropy in the region, less than x naught. Sorry, there should be an x naught. Okay. The next fact that we'll need is that for a cut like what we have considered here, just a regular cut of some 2D of a spatial line, the vacuum subtracted modular Hamiltonian has a nice local form. It's just the integral of the stress tensor with a boost weight x naught minus x. So this is a well-known result. And then we'll need the usual statement of monotonicity of relative entropy, which just says that for an arbitrary x, a cut x, then if I take a derivative of the relative entropy with respect to x, it's always going to be positive. And again, let me just emphasize, whenever I mention derivatives here, I imagine derivatives where we move the cut to the right. We take our cut and move it to the right. And then we'll need the Kunik. So the Kunik is just the statement in this context that the second derivative of the relative entropy with respect to x is also positive. And lastly, we will need Strong's of additivity, where I've written Strong's of additivity here in a just a very special form where I'm just going to consider intervals that are defined by taking my point x naught and just adding a little bit delta to it, because eventually we're just going to consider what this statement tells you about derivatives of the entropy with respect to x naught. So these are some facts. Don't worry so much about memorizing all these facts right now, because we're just going to need to use them in very specific ways. So So we're going to use these facts. Let's see what we can learn about this state. So strong subadditivity in the limit that delta goes to 0. So if we just expand strong subadditivity or to first order in delta, gives us this first inequality here. Oh, sorry, inequality. It tells us that the derivative of the entropy of the state less than x is always greater than or equal to the derivative of the entropy of the state greater than x, all evaluated at x naught. And monotonicity of relative entropy, so the third statement here, if you write out relative entropy in terms of the modular Hamiltonian and the entanglement entropy, and you use this local form of the modular Hamiltonian, it tells you that the integral of the stress tensor from -infinity to x naught is always greater than or equal to the derivative of the entropy that's less than x. So we have this twofold inequality coming from SSA and monotonicity. Now, the optimizing state satisfies the following statement. It satisfies the fact that the derivative of the relative entropy evaluated at x naught is equal to 0. So this just comes from its definition. If the optimizing state, you can just drop the infimum because it's the exact infimizing state. So you have derivative of the entropy is equal to the energy, which is the same as saying that the derivative of the relative entropy in this first statement is just equal to 0. All of this is happening at x naught. Okay. So the fact that the derivative of the relative entropy vanishes at x naught is actually a very powerful constraint, because we can now apply monotonicity and Kunik to conclude that the derivative of the relative entropy, if it vanishes at x naught, has to vanish everywhere to the left of x naught. So the way you see this is just that, so monotonicity tells you that the derivative of the relative entropy has to decrease as we approach x naught from the left. On the other hand, the Kunik, which is the statement that the second derivative of the relative entropy is positive, tells us that the relative entropy, the derivative of the relative entropy has to actually increase as we approach from the left towards x naught. So monotonicity says that that S prime rel has to decrease to 0, whereas Kunik says it has to increase to 0. The only way both of these statements can be true is if the derivative of the relative entropy was just 0 the entire time. And this is, again, true everywhere for x naught less than x. I'm sorry, for x less than x naught. Okay. So let's just take a pause and appreciate what this statement means. So this tells us that the relative entropy is just constant. Relative entropy of the state with respect to vacuum is just constant everywhere for x less than x naught, which is highly suggestive of the claim that the state for x less than x naught is just a vacuum. So in other words, the energy minimizing state, the state with the smallest energy, to the left of x naught, given knowledge of the state on the right, is just a vacuum state, just a state with 0 energy. So the reason for this is just if the relative entropy is constant, no matter how much I move to the left, then we're not learning any new information about the state compared to the vacuum. So it's highly suggestive of the fact that, since we're not learning anything new compared to the vacuum, it's always just the vacuum state that we're putting in there. So the stress tensor there just vanishes. So this is a heuristic argument. We have a much more detailed argument for why this is the case that makes use of some, various entropy energy relationships, but they're not particularly illuminating. The intuition really just comes down to this. So the relative entropy is not changing. We're not learning anything new, so it really should be the vacuum state. And notice that if this statement is true, that the stress tensor is just 0 for x less than x naught, then that means there has to be a delta function in the stress tensor at x naught, right? Because so the entropy variation here is non-zero, and then the entropy variation to the left just goes to 0. Because if T is equal to 0, then we learn from this that the entropy variation itself is also equal to 0, so that there's a jump in the entropy variation. And this jump in the entropy variation from this relationship has to be sourced by a stress tensor shock. Okay. Okay, let me just. Yeah, sorry.
Can you expand on this delta function? Like it's some sort of this delta function is some sort of a firewall, basically, or how?
Yeah. So okay, that's a good question. I will mention this a little bit at the end. So this is an integrable shock. So it's not a firewall per se, in the sense that, so it depends on what you mean by firewall. If by firewall you mean like an infinite energy barrier, then this won't be a firewall. This is a finite energy shock.
Okay.
Yeah, so this is a finite energy shock, and it's pretty interesting that it shows up. It's more interesting to consider what the shock means when we apply it to black holes. So it's going to be pretty important for the black hole context. And then when I talk about the states that Ceyhan and Faulkner considered, then I'll mention firewalls, because something interesting happens there as well. But this is just an integrable shock with finite energy. Yeah.
So basically what we have is on the left-hand side, we have the vacuum state.
Yeah.
We have a resistance symmetry for the vacuum, and we glue it to some other state, as far as I understand, right?
Exactly. And the gluing, yeah.
And the only thing that we know about this other state is the derivative of S.
Yeah, exactly.
And you say that then the energy minimizing state is the one in which there's a discontinuity in the energy density at the gluing place.
Yep.
And then it's the vacuum. Okay.
Yep, exactly. Yeah.
And this state is somehow like how to say it, robust from the point of view of, say, algebraic quantum field theory and so on and so forth, or?
So it's not. Yeah. Okay. It's not quite. If by that do you mean like can you make sense of this for type 3 algebras?
Well, I mean, I'm not an expert, but I mean, I know that people there in this community are very careful, and like when I see divergent points like energy density, I mean, it makes me suspicious.
Yeah. So there's this the construction that Faulkner and Ceyhan consider is an algebraic construction that only ever makes use of relative entropy. But if you want to see the shock show up, if you want to ask what is happening to the entropy of the state and see the shock show up, then you have to assume that there's some sort of factorization of the Hilbert space, and you have to sort of demote yourself down from type 3.
Okay.
So I don't know if it's robust from the point of view of algebraic quantum field theory, but I can give you an argument later for why even in algebraic quantum field theory, if you ever want to consider the gluing of two states in this way, you just need to have this shock. There's no other way around.
Well, and like this
it's
is not
essentially implied by the GNS construction.
This is not the state that has infinite energy, right? Because delta function, as you said,
yeah, it's not infinite energy.
Right? Yeah.
Okay. Yeah. You can show that the state has a finite average null energy. So it doesn't have infinite energy anywhere. Yeah. It's just a finite energy shock.
Okay. Thank you.
Yep. Okay. So just briefly mention. So far we've been talking about 2D, the 2D case, but there's not much more to say about the higher dimensional case. You basically just, it's the same story except so if you now you might null. So imagine I have a null surface. So far we've been talking about a spatial interval like this. Now imagine the spatial interval is actually a null interval. Because the reason we want to talk about a null surface is this. One of the things that we use. Sorry, I'm going back and forth so much. One of the things we used is that the modular Hamiltonian has this local form as the integral of the stress tensor. And in higher dimensions, this statement has only been proven for arbitrary cuts of a Rindler horizon. So we only know this statement to be true on a null surface. So for higher dimensions, you have to restrict yourself to a null surface. And now what you imagine is you have an army of ants that walk down from -infinity on the null surface up to some cut of the null surface v of y, where y are just the transverse coordinates. And then you just do the same exact thing where you minimize the total energy below the cut by essentially just minimizing the average null energy on each of the null generators separately. And then you can run through the exact same story as before. Nothing exciting happens compared to before. And you find that there is a shock of the stress tensor at the cut v of y, which is going to be our entangling surface. And it's just given by the entropy variation with respect to that cut. So that's just as an aside. Okay, so now let's come back after that detour. Let's come back to the original thing we were interested in, which is what is the coarse-graining prescription for the quantum marginally trapped surface? So it's like the evaporating black hole case. Okay, so this blue line here represents the Q screen that's slowly converging to the event horizon. This point V naught, hopefully you can see that, is the quantum marginally trapped surface. So I'm going to consider the outer wedge of V naught. So which again just means there's some partial Cauchy surface that's anchored to the boundary, and just consider its domain of dependence. And then from V naught, we're going to try to find a state which saturates that inequality from before, that the generalized entropy is always greater than or equal to the generalized entropy of the quantum extremal surface. Okay. So we're going to consider perturbations of the Killing horizon. So to start with, because it's a quantum marginal surface, marginally trapped surface, it has capital theta k equal to 0, just by definition. Okay, so here's the important thing. So the shock that we found before. So now we're gonna so now we're gonna imagine that the state on this partial Cauchy slice is the state that we obtained from energy minimization. So we're gonna say that this ant is walking down up to V naught. It knows everything about what's in the outer wedge, and then it puts the energy minimizing state in the inner wedge. We can do this. So we can just apply everything we learned about the energy minimizing state to this context, because it's a Killing horizon. And on a Killing horizon, the modular Hamiltonian also takes a local form. As long as you have any Killing symmetry, you can write down the modular Hamiltonian as a local integral. So we're gonna put the energy minimizing state on this background. And we know from what we just talked about that the energy minimizing state has a shock at V naught. And the shock, right, just to remind you, is a derivative of the entropy. So it's a stress tensor, which is the derivative of the entropy. You can show that the shock actually simultaneously sets both the derivative of the entropy equals 0 below V naught and the classical expansion theta k equal to 0 below V naught. Okay, so the reason it sets the derivative of the entropy equal to 0 is what we had just discussed. That is the whole purpose of the shock, right? It shows up because the entropy derivative is 0 to the left. The reason it sets the classical expansion equal to 0 is due to the classical Raychaudhuri equation. So the classical Raychaudhuri equation for perturbations to a Killing horizon, so that's what we're considering here, right? Perturbations to a Killing horizon. It says that the derivative of the expansion is just equal to the stress tensor. So now imagine integrating the left-hand side of this around some tiny ball, like some tiny interval around V naught. So if we do that and use the fact that there's a jump in the stress tensor at V naught, combined with the fact that the capital theta k is equal to 0 at V naught, you can show from this that the discontinuity in theta k actually sets theta k equal to 0 below V naught. Now, because theta k is equal to 0 below V naught, and the entropy variation is equal to 0 below V naught, this overkill statement tells you that capital theta k is equal to 0 everywhere below V naught. So we have a quantum stationary surface. Okay, so this is already looking very similar to what Netta and Aaron found. where except they had little theta k equal to 0. Now all we do is we need to find a quantum extremal surface. Okay, so the way you do this is you just keep evolving back into the past until you hit a surface which has the classical theta L equal to 0. So the classical expansion in the L direction, in the ingoing direction, we know that that eventually has to go to 0 because this is just a perturbation to a killing horizon, and the classical part of theta L is already non-zero for a killing horizon. So eventually it has to go to 0. And then, because we're just considering tiny perturbations around that, we know that if we keep evolving that back past theta L equals 0, we'll eventually hit a surface for which theta L will cancel out the derivative of the entropy in the L direction. And it's just going to be some Planck length separated from the classical extremal surface. So this is just the claim that if I have perturbations to a killing horizon, then there will always be a quantum extremal surface that's somewhere a Planck length close to the classical extremal surface. And this gives us a quantum extremal surface. And because capital theta k is equal to 0 everywhere, the generalized entropy is constant everywhere along this null surface to the past. So that tells us that the generalized entropy of the quantum extremal surface has to equal the generalized entropy of the quantum marginally trapped surface at sigma. So we've achieved the exact same construction as Netta and Aaron, but at a quantum level. And the way we achieved it is through this energy minimizing state. So it's kind of amazing that this completely different problem of just asking what is the minimum energy the inside of a black hole, in the context of this perturbation to a killing horizon, gives us a state which maximizes our ignorance of the generalized entropy of the interior. So the slogan then is like the energy minimizing state is actually doing the coarse graining for us in the context of like quantum fluctuations on a killing horizon. And this gives us a boundary interpretation of the generalized entropy of some cross section of this Q screen. So it's some dynamical event horizon, and it tells us that the boundary interpretation of it is actually the von Neumann entropy associated to this auxiliary state that we've just constructed by doing the energy minimization.
A question. So in the derivation that you showed in previous slides, you were using the modular Hamiltonian for the vacuum state.
Yeah.
Of course, over here you're talking about the curved space-time, so the modular Hamiltonian is different. But I mean, shall I understand that you're just using the properties of the vicinity of x naught or whatever I can see it there, so that like you try to think of the quantum state there as being approximately the vacuum, or how shall I think
you can do that, and it will go through just fine. But what I actually have in mind is the global vacuum here is the Hartle-Hawking state. So instead of having the vacuum in the quantum field theory context here, I just imagine I have the Hartle-Hawking state of my quantum fields on this fixed background. And the modular Hamiltonian, the vacuum subtractor modular Hamiltonian is going to be defined with respect to the Hartle-Hawking state at some fixed temperature.
Okay, but I thought that the whole point here is to consider dynamical black holes, right? So like, does it make sense to talk about Hartle-Hawking state for dynamical black holes?
No, so the vacuum state would be where like so I wouldn't have any flux, like I'm not throwing in any perturbations for the vacuum state, and I'm starting with the killing horizon. Yeah, so I'm fixing the background to be a killing horizon.
No, agreed then. Yeah. Okay, thanks.
Yeah, no problem. Okay. Yeah. So yeah, just to because of that question, I just want to emphasize that this is showing that the energy minimizing state gives you the coarse graining for perturbations to a killing horizon. But of course you can ask, okay, so what about for a completely, non-stationary black hole? So not for perturbations to a killing horizon, it could be some totally non-perturbative state where it's far from stationary. And And this is essentially the question of what is the boundary dual of a generalized entropy for surfaces that are much more general than just cuts of these perturbations to Killing horizons. Okay, so here, I'm just going to start out with a conjecture. The conjecture is that for any quantum marginally trapped surface, there exists a state that we can fill in the interior, which has simultaneously the classical expansion equal to 0 and the entropy variation of the matter fields equal to 0. So this is just a conjecture, and it's simply motivated by what we've just learned for perturbations to Killing horizons. For the perturbations to Killing horizons, we've seen that we can actually explicitly get this state from the energy minimization. So here, I'm just going to conjecture this. And actually, these two statements are all you need to show that there exists this stress tensor shock that is there at the cut. This is just a conjecture. Let me try to, in the last 10 minutes that are left, let me try to motivate a way towards actually proving this conjecture. But we're far from proving it, but let me try to actually give you some way to get at it. Okay. So this is something we're still working on, but let me try to give a more constructive approach to these states that saturate so these states that actually give you the coarse graining, where we fill in this stationary null surface to the past. Okay, so I have my null surface, which I'm going to call NK, and it has some affine parameter lambda that is defined everywhere on the null surface. I'll call that lambda. And then what I'm going to do is I'm going to take my marginally trapped surface sigma. This is all at the classical level right now, and then so this is all purely classical, and then we'll get to the quantum case in a second. So I'm going to rescale the affine parameter below sigma. I'm going to rescale it in a way where I'm just going to say lambda goes to e to the s lambda, where s is just some real number. After doing the rescaling, I'm going to glue it back to the null surface that's above sigma, where I haven't done any rescaling. So this is just a simple coordinate transformation that I've done, but now I'm going to demand that in this glued back null surface, lambda is still an affine parameter everywhere. So essentially what this is doing is saying, okay, so for the null surface above sigma, don't do anything. For the null surface below sigma, take some evenly spaced intervals and then just squish them some more. Because when you do a rescaling of lambda by this dilatation factor e to the s, you're just squishing your intervals. And then when I glue these two null surfaces back together, and then demand that the new affine parameter, that the new parameter lambda is just an affine parameter everywhere, what I've essentially done is stretch the state below sigma. So I glue them back, demand lambda is affine everywhere, despite me having done this rescaling, and now I've produced a physically new configuration where the state below, so if this little blob is some matter field, gets stretched out. And the claim, which is actually pretty easy to show, is that at the classical level, in the limit as s goes to infinity, the limit of this stretching prescription as s goes to infinity is the coarse-grained state. So at the classical level, we can prove this pretty easily. Essentially, all the properties that we need in order to get the state, the coarse-graining state, the stationary null surface, it just automatically pops out in this limit. At the semi-classical level, it's much harder to show that this is the case, and this is what we're still working on. But let me give you some evidence using holography that something like this is really what's happening in the coarse-graining prescription. And then I'll just end with that. Okay. So let's say now we have some ADS CFT set up. And what I'm going to do is take the RT surface and consider the inner wedge. I'm going to consider this NK surface right here shot out from the RT surface. So imagine sigma to be the RT surface. Okay, so there's a constraint equation for the shear of the RT surface, and the details are not so important, but you can show that this procedure that we've just defined here, this like gluing procedure with the stretching, produces a shock of the Weil tensor. And the shock of the Weil tensor looks like the following. So this Weil tensor is contracted with the two null vectors. With the null vector k, that the same k that's tangent to this null surface direction. And you can show that the jump is given by the shear sigma of the null surface, evaluated at the RT surface, times the delta function of the RT surface, because the shock. And then there's this prefactor 1 minus e to the minus s. Okay, so this just comes from integrating the shear evolution equation. And then what you can do is use a Pfefferman-Graham expansion around the ADS boundary, and then work in some expansion around, like in some coordinate, around the ADS boundary, and show that this Weil tensor shock, if you evaluate it near the boundary and use the Pfefferman-Graham dictionary, it actually gives you the following shock here. It gives you a shock of the stress tensor, which is just the entropy variation, times this factor 1 minus e to the minus s. This shock is actually notice if you take s to infinity, it gives back the shock that we found for the energy minimizing state. And for finite s, for non-zero s, this is actually the exact same shock that was obtained by Ceyhan and Faulkner in their like explicit construction of the energy minimizing states, where they basically just do a one-sided modular flow. So what they do is they have imagine instead of the bulk, this is all happening on the boundary, and they just do a one-sided modular flow below sigma that essentially just boosts everything. And in the limit as s goes to infinity, imagine s is some modular parameter s, as s goes to infinity, that the limit of that infinite boost produces this shock. So all we're doing is giving a bulk version of this, where instead of doing modular flow at leading order, you just do a one-sided boost at the classical level. And then because this is highly suggestive, this holographic calculation is highly suggestive of the following statement, that the one-sided modular flow on the boundary that Ceyhan and Faulkner do is dual to this stretching prescription that we've given in the bulk. So if that duality is true, then it's highly suggestive of the fact that in the bulk, if we have a black hole, let's say, the coarse-graining for a semi-classical state is essentially just take sigma to be quantum marginally trapped surface, do this stretching prescription at the classical level, and then do a boost of the quantum state that's also one-sided, probably using the one-sided modular flow in the bulk. So it's sort of like JLMS. This is just preliminary. I mean, we're still working on all the details of this, but the evidence seems to be pretty strong that this kind of duality exists. So let me just summarize very quickly. So we defined a coarse-graining procedure for semi-classical black holes that landed us on like a prescription for getting at the generalized entropy of a quantum marginally trapped surface in holography. Then we talked about like various properties in quantum field theory of energy minimizing states, and then showed that these energy minimizing states are all you need in order to define a coarse-grained entropy for a black hole that's like a perturbation of a Killing horizon, quantum perturbations of a Killing horizon. And then we discussed some ways of possibly explicitly constructing these states, both at the classical level and at the semi-classical level. And there's a bunch of questions that I think are interesting to think about moving forward. So I talked about some evidence using holography that the like one-sided modular flow on the boundary is dual to this like stretching prescription in the bulk that gives you the coarse-grained state, at least for the RT surface. And even more evidence for this stretching prescription would be if we could talk about it using Randall-Sundrum branes in holography. So if you imagine instead of at the ADS boundary, you're at some finite cutoff surface that's actually a Randall-Sundrum brane. And you imagine doing this stretching prescription for a bulk RT surface that's anchored to a marginally trapped surface on the RS brane, it would be nice to see all the properties that we talked about come out naturally in that context. And I think there's an interesting connection to be thought about between these stretching states that we defined, with this rescaling of the affine parameter, and this question of what is the non-perturbative prescription for JLMS. So when I say JLMS here, I just mean the statement that the boundary modular flow equals the area operator in the bulk plus the bulk modular flow. If you notice this stretching prescription that I defined here, you can also think about it as just like, imagine you have the RT surface. The area operator classically acts like a boost around the RT surface. So we're essentially just doing a one-sided version of the area operator, where you just boost one side of the RT surface and not the other side. So it's sort of like JLMS if you now ask what happens at the semiclassical level. And this Weil-Schock calculation that we have seems to be suggesting that, non-perturbative JLMS maybe makes sense, and it makes sense through this kind of stretching prescription. I mean, there's various subtleties here, but the main hurdle to get around is essentially like, what does relative modular flow mean non-perturbatively in the bulk, when your two states that you care about, like the vacuum and some excited state, are very far away from each other. And that's very important for this coarse-graining problem. Okay, and then of course there's the ultimate question, which is, what does a generalized entropy even correspond to on the boundary for an arbitrary bulk surface, even if it isn't just a cross-section of some black hole horizon? Okay, thank you.
Thanks a lot. Are there any more questions from other people online? Yes.
I have a question. Is there some connection or useful application of what you were presenting and recent works on page curves in semiclassical holography?
Yeah, that's a good question. So actually, one thing that's kind of important to understand is how this coarse-graining prescription works in the context of these page curve calculations, because one important thing there is the quantum extremal surface is very far away from the classical extremal surface. Right, the whole point is that there's this phase transition that happens.
Yeah.
So you can't perturbatively solve for the quantum extremal surface around the classical one. So if there was a way to prove that the quantum extremal surface prescription always works in general, even if you don't just consider perturbations around classical extremal surfaces, then I think this coarse-graining prescription should automatically just give you the page curve. But I'm not sure it gives you more insight than what they have already found. I think it's dynamically what the page curve is for a, instead of a event horizon, it would be for like a one of marginally trapped.
Thanks.
Other questions? Okay. If not, then let's thank Ben again for the very interesting talk.